This is FE Peer Review. The date is the 11th of February 2024. The azimuthal equidistant projection and a small correction to an earlier video. In my last video on map projections, we looked at the Lambert equal area azimuthal projection, which we see here on the left. And today we're going to look at another azimuthal projection, but this one is an equal distance projection. So I'm going to quickly touch on the small mistake in my earlier video and correct it, and then we'll move on. So at the 6-minute 16-second mark here in my video called Brian Leakey Star Rotation is Bogus. So at the 6-minute 16-second mark, I went off in the wrong direction here and made a mistake, which was caught by one of my viewers, Michael D. Amelson. He said, "You start explaining how the projection is made by rolling the spherical Earth on a flat plane." What I had described was putting a sphere on a tabletop and then rolling that sphere, and where each of these points touches the tabletop, that's where they end up on our map. That was in fact incorrect. That is in fact the way it works for the projection we're going to be looking at today. But the previous video, what I should have said was, what you're doing is you've got your central point, which is where the sphere touches the tabletop, and then you're drawing an arc with its center at that point, and then you're bringing points down using an arc. So all of these points have an arc that originates at the point where the sphere is resting on the table. So if we take this one up here in the upper right, that arc has its center down here where the sphere is resting on the table. And if we take the polar opposite point and cast an arc to the table surface, it has its center point where the sphere rests on the table. So obviously, if you take a look, for example, at the distance from this point on the sphere to the, let's call it the North Pole on the sphere, that arc distance there is much longer than the distance on the tabletop surface. And so that is the way the Lambert equal area projection works. And I think I want to touch on one other aspect of the equal area projection just to make sure it was clear. I've taken one version of it here. I think this is the same version we looked at before. And I want to describe why it's called equal area. You can see that I've drawn a four-sided figure in red here with the upper edge of that figure right on the equator line that's passing through this flat map here. That area described by those four sides is the same area as the one we see further to the left. Now the shapes are very different. There's a lot more distortion out towards the edge, but the surface area is the same, and that is the Lambert azimuthal equal area projection from last time. That's what the equal area is referring to. If we look at the northern hemisphere, we've got one outlined in green and another outlined in green. Those on the flat map have an equal area, and on the globe have an equal area. So they are equal and consistent in terms of surface area, but we're seeing, of course, shape distortion, considerable shape distortion. But now we're going to move back to today's subject, the azimuthal equidistant projection. This type of projection probably goes back all the way to the ancient Egyptians, who did not use it for the earth, but rather did use it for the sky. There are apparently some Egyptian star maps that appear to be based on this kind of projection. But the earliest example or use of it that we know of for an Earth map was by none other than Al-Biruni, used the projection to make a map like this. And what we see here is that it's an equal distance map. So these white circles are 15-degree latitude lines. We've got 0 at the center, 15, 30, 45, 60, 75, 90, and the red one is the equator. Then they continue out in 15-degree increments. I've drawn 3 red lines here. Each of those 3 lines is the same length on the map and the same length on the Earth. So when you follow a longitude line from the rim to the center, you have correctly scaled distances. And also, I've drawn a green arrow pointing to the center. If you're following a longitude line, this map gives you the correct azimuthal angle. so no distortion in the azimuthal angle. Now, what you'll see is that the areas are all screwed up. This is not an equal area map by a long shot. These, for example, this little triangle here right at the center has an equal area to the shape out here at the rim in reality on the globe, but not on this map. This is called the Tissot's indicatrix, and it's a way of describing the distortions geometrically. Each of these orange blobs is supposed to be a circle, and if we look at the center of the map, we see a perfect orange circle. The extent to which that circle turns into an ellipse shows us the amount of distortion on the map. So as we move towards the edge of the map, we see that these circles become stretched out in one axis into becoming these long, skinny ellipses. So I'll call it the horizontal axis, remains the same as the original circle at the center. There's no distortion in that dimension. That's the equidistance dimension. But the perpendicular axis to that becomes extremely distorted. So that's your distortion indicatrix there. And I'm going to fiddle with opacity a little bit so you can kind of see how these go together. Here's another version of the same projection, the azimuthal equidistant projection, and this time we've placed Antarctica at the center. So this tells you your azimuth, straight shot down to Antarctica, and if you follow a longitude line to get there, you can get your distance off of it. Just don't try using it to navigate around the edges. This is, by the way, everybody's favorite flat Earth map and the source for the United Nations logo. And let's end with one last pretty picture. No, not that one. Excuse me. That's not the one I meant. There we go. Isn't it lovely? I picked it because it has a pretty good view of Antarctica. Now you may recognize it as the Apollo 17 blue marble photo, but if something looks a little bit odd, well, yes, this is not the way most people are used to seeing it. This is, in fact, the way that the astronauts saw it. Antarctica was at the, quote, top. Of course, there is no top. Putting north at the top is a convention in our world. This is the way they saw it. But when the photo was published, it was rotated so that Antarctica was down at the bottom and everything was just the way it's supposed to be, with the northern hemisphere on top. Anyhow, I just wanted to share that lovely image with you as it was originally seen. That's all. That's enough, and I hope you enjoyed this. Remember, there's a like button down there and a place for comments. And I always welcome new subscribers. So have a great day, and I'll see you again soon.